Hi there, my name's Lauren Madigan. I completed the HSC in 2012 and received an ATAR of 99.65 as well as first in the state in HSC mathematics. I'm here to help you try and get a better understanding of some of the main concepts that may present as difficult throughout the year. Today we're going to take a quick look at the basic algebra and arithmetic and then move on and focus on plane and coordinate geometry. And the first thing I'm going to have a look at may seem intuitive to many of you, but what's really important is being able to recognize it in the context of a harder question. So here's a look at some basic formulas that you may have been familiar with since the start of Year 11 and even earlier. Like I said, while many of them look familiar, what's really important is being able to recognize them in a harder exam question, as you'll be amazed how many times simplifying something as basic as this can lead you closer to the answer. Looking down especially at those here in green, you can see a quick way to remember them is known as SOAP. So here, looking at the case of x cubed minus y cubed, we've got a negative sign. So then we've got the same sign, the opposite sign, and an always positive sign. So that's mirrored by your SOAP. Here, just to confirm that, we've got a positive sign. So same, opposite, always positive. So like I said, just keep these in the back of your mind throughout your HSC course, and you never know when they may come into handy. So now I'm going to move on to some line and plane geometry. The first thing we're going to look at is some basic properties of lines, and again, while many of these may seem obvious, what's really important is being able to recognize them in a much more complicated question, as it'll help you simplify the answer and get much closer to that result. So vertically opposite angles, we know that these are always equal, whether the lines, no matter what angle those lines are intersecting in, the angles here represented by x, these will always be equal. But once we go to parallel lines, we get a few special rules. So the first of these is that on parallel lines, alternate angles will always be equal. That's represented by the green x's and the yellow y's to the right. Also on parallel lines, your corresponding angles will also be equal. Again, this is clearly shown on the diagram, provided as long as those orange lines are parallel, the 110 degrees will be equal in both of those spots. Another thing that can come quite in handy is that your co-interior angles are supplementary on parallel lines. And this means that they add to 180 degrees, and they're shown there by the two yellow lines. Now, what if we were asked to prove that two lines were parallel? Well, this easily follows from what we just discussed. So all we need to do is to show that either the alternate or corresponding angles are equal, or the co-interior angles are supplementary. Another thing to keep in the back of your mind when you're working through these kind of geometry problems is that if two lines are both parallel to a third line, then the three lines must be parallel to each other. You may see this pop up in examples from time to time. Now we'll go have a look at some types of triangles. While this probably isn't the most common thing to be asked directly in a HSC question, again, knowing it can only help you in the context of a more complex question. So the first type of triangle I'll look at is the scalene triangle. This has no two sides or angles that are equal. Then we've got a right-angled triangle. This contains one 90-degree angle, and the longest side is referred to as the hypotenuse, denoted here by C. An isosceles triangle has two equal sides, and hence its base angles will always be equal, as shown in red. Then, an equilateral triangle, as you're probably familiar, has three equal sides and three equal angles, while an acute angle has all of its angles acute, and an obtuse angle is a triangle that contains one obtuse angle. Another rule to keep in the back of your mind as you're working through these questions is that any line joining the midpoint of two sides of a triangle, say from this point here to this point here, is not only parallel to the third side, but also exactly half its length. That can be quite helpful when trying to prove many things. Quick look at congruency and similarity. So we've got 4 tests for congruency. The first of those is 3 equal sides, so it's referred to as SSS, and obviously if 3 of the sides are equal, then your triangles are exactly congruent. We can also have two equal sides as long as their included angle is also equal. We can have two angles the same and one side equal. Now that does not matter which side it is in relation to the two angles. And we can also have a right angle in each triangle, an equal hypotenuse, and as well as one additional side angle. All of those should give you complete proof that you've got a congruent triangle. Now looking at similarity, we've got three proofs that we can use to show that a triangle is similar. So we can say that the three pairs of angles are equal. Now this does not mean that it's congruent. We have to be careful here because the sides may be in proportion with equal angles, but not necessarily exactly the same. Saying that, three sides in proportion is your second test for similarity. The third test is that two sides are in proportion and the included angle is equal. And this is shown here, that while those angles are all the same, your triangles are not necessarily congruent. Another thing that pops up in geometry is the ratio of intercepts. So when two or more transversals cut the parallel lines, the ratio of the intercepts will also be equal. So here we've got our ratio of PQ to QR is going to be exactly the same as JK to KL. Another thing to keep in mind. Quick recap of some angle sums. Again, many of these you may be familiar with, but if there's something you haven't covered, you may want to jot it down. So the interior angle sum of a triangle, probably where is 180 degrees. Any quadrilateral will be 360 degrees. And the exterior angles for any polygon will be 360 degrees, where a polygon is any n-sided figure, where n is just an integer. The interior angles of a polygon in general will be 180 times n minus 360 degrees, where n is the number of sides. And we know that the exterior angle of a triangle is equal to the sum of the opposite interior angles. Now we're going to look at a few shapes specifically and the proofs that can be used to identify these kind of shapes. Now that does quite often come up in a question, and it's very important to be familiar with these. So the first of these shapes we're going to look at is the parallelogram. So this is a quadrilateral that has opposite sides parallel. There are several properties of a parallelogram that are essential to know in order to prove that something is in fact a parallelogram and allow you to use these properties to solve the next parts of the questions. So we'll have opposite sides equal, opposite angles equal, the diagonals will bisect each other, and also bisect the parallelogram into two congruent triangles. So how do we prove that something is a parallelogram if we were asked to? It can have two pairs of opposite sides equal, two pairs of opposite angles, one pair of opposite sides both equal and parallel, or if the diagonals bisect each other. Now we'll look at a rectangle. So these shapes can quickly build on from one another, mostly falling back to that parallelogram. So a rectangle can be thought of in terms of a parallelogram with one angle, a right angle. So its properties include all of those of the parallelogram, and in addition, its diagonals are equal. So how to prove this? If the diagonals are equal, then it's a rectangle. Now we're going to move on to a rhombus, and again we're going to take this back to the parallelogram. So a rhombus can be thought of in terms of a parallelogram with two adjacent sides equal. Again, the properties include all of those of a parallelogram, plus some additional things. So the diagonals will bisect each other at right angles, as shown in the diagram, and the diagonals also bisect the angles of the rhombus. Very important facts to keep in mind. To prove that something is a rhombus, there's many ways we can do it, and this is actually quite a common exam question, and they will sometimes only give you enough information to do it one of the three ways. So I would highly recommend being familiar with these methods. So we can show that all four sides are equal, that the diagonals bisect at right angles, or that one pair of opposite sides are equal and parallel, and that adjacent sides are equal. So this third proof follows straight from the definition of a rhombus from the parallelogram. Helpful to keep in mind. Moving on to the square. The square comes from a rectangle, and that's a rectangle with a pair of adjacent sides equal. Its properties are all of those of the rectangle, as well as its diagonals are perpendicular, and the diagonals make angles of 45 degrees with the side. Some quick miscellaneous shapes before we move on. Trapezium has one pair of parallel sides. A kite has two pairs of adjacent sides equal. Now again, many of these previous notes may have seemed quite obvious or basic compared to some of the topics you're doing now, but like I've said many times already, we really need to be quick on being able to recognize these things in a harder question. But we'll do an example at the end. So some quick area formulas that you should be familiar with, and again, many of these may not be provided when you need it most, so good to just keep them in mind. Your square is simply the length of one of the sides multiplied by itself. Your rectangle is your width times your breadth. Triangle, half base times your height. Circle is pi r squared. A trapezium is half your height plus the sum of your sides, and a rhombus or kite is half xy, and that's where x and y are your diagonals. And your parallelogram is simply your base times your height, or your two sides times the angle between them. Some quick volumes to know. These are presented here for the sphere, and we've also got the surface area. Then for the cylinder, now be careful with the surface area of the cylinder. If your cylinder has no lid or base, then we won't include the 2 pi r squared. Similarly with the cone, if your cone does not have a lid, then your surface area will only be the pi r L, where L is the slant height. If your cone does in fact have a lid, we'll need to add the pi r squared to this formula. Now we're going to move on to line and coordinate geometry. It's very similar in the types of skills that have to be applied, and the topics are often covered around the same time, so hopefully this will follow on nicely. So two very important points that you're probably familiar with is your distance between 2 points and the midpoint of 2 points. So I've got the formulas there for you, but most of these questions are pretty straightforward. You'll often see it about question 2 if you look through the past papers, and there'll be about 1 or 2 marks each for this kind of question. Then we'll have a look at gradients. So gradients, they're often represented by the letter M. So we can find a gradient if we're given 2 points simply as the rise over the run of that line. It's also possible to find the gradient given the angle of the line, where the gradient is simply tan theta. But an important thing to note here is that your angle is always the positive angle. So I've tried to show this on the diagram here, that if you have a line with a positive gradient, then your angle here will be theta. But if your line has a negative gradient, then your angle now covers this entire range. So it's always the angle in that positive direction. With the lines and the gradients, there's several ways in which these can be represented, and they all have different uses, and sometimes you may be asked specifically for one over the other. So it's important to be able to recognize the different forms and which form may be most helpful for you when trying to answer a particular style of question. So the first form is your gradient intercept form. So it's your y equals mx plus b. Here m, as we said before, is the gradient of the line, and b is the y-intercept. Your second form of the line is known as the general form. So this follows directly from a rearrangement of the gradient intercept form, but you can be asked for something in general form, so it's important to know how to display that if required. Your third form of the line is the point gradient form. So as suggested by that title, it's useful when you're given the point and the gradient of a line. But instead, if you were given only 2 points, remember back a few slides, we can find the gradient of the line from those 2 points using the rise over the run, and then use this gradient and one of the points, it doesn't matter which point we choose, to find the equation of the line. So here is your point gradient form. x1, y1 is simply one of your points. Again, as I said, if you're given 2 points, it does not matter which point you use. You can test that out for yourself, and m will be the gradient. Alright, moving on to some properties of the lines. So we've got parallel lines. The distinguishing feature is that their gradient is always the same. So that can be represented as m1 is equal to m2. So it's the gradient of the first line is equal to the gradient of the second line. But the lines are not necessarily equal. Perpendicular lines, the gradients are the negative inverse of one another. So it's quite handy to know that when multiplied together, they can give a value of -1. Sometimes a useful result that can fall out in a few of the proofs at the end of, they tend to add that on to one of the end of these coordinate geometry questions. Another thing that may be asked, and I think this mostly comes up in the 3-unit papers, but we've got tan, the angle between two lines. So it's equal to your first gradient minus your second over 1 plus the sum of that, and the absolute value of that result. Now I can't quite recall whether that is required in the 2-unit course, but you know absolutely everything to be able to do that, and sometimes it's very handy to be able to find the angle between two lines in answering a question, so it's a very good formula to have on board. Moving on to the equation of a circle, we know that if circle's at the origin, we've got x squared plus y squared is equal to the radius squared. So if we're given that line, we simply square root the numerical value over here, and we can find the radius of that circle. If your circle is not at the origin, the formula rearranges to give x minus a squared plus y minus b squared equal to the radius squared. And here, if we've got the circle in this simplified form, AB will be the centre of the circle, and again R will be the radius. Perpendicular distance. Now this probably comes up in almost every single one of the papers. It basically represents the shortest distance from a point to the line and is always at 90 degrees to the line. Now luckily there's a very convenient formula, and as long as you're familiar with it, usually this question will present no problems, and again is probably a bit earlier on in the paper unless they've put a bit of a trick on it. So here's the formula that many of you may be familiar with already. Your A, B and C, these come from the general form of the line that we discussed earlier, and again x1 and y1 is your point, as you can see on this diagram. So I've just got that there summarised there for you. So a quick trick to watch out for with the perpendicular distance. I haven't seen it in a past paper, but it may pop up. So if we've got that the distance from one point to the line is the absolute value of 5 over 7, coming straight from our formula on the previous slide, and the distance from a second point to that same line is negative 5 over 7, we can get an interesting result. Now because this is the absolute value of 5 and negative 5 respectively, our final answer is going to be the same and simply equal to 5 over 7. But what this actually proves, if we stop at this point of the question, is that these points will lie on the opposite sides of this line. Handy thing to keep in mind. Lastly, we're going to look at the equation of a line through the intersection of two other lines. So there's two methods to do this type of question. The first way is simply through simultaneous equations, through rearranging your x and y and solving for that point, and then going back and using the point you were given, the point you found, making the gradient, and so on, all was discussed in the previous slides. But the method I'm going to show you now is known as the K method, something you may or may not be familiar with. So on the next slide, we'll do a quick example. So if we were asked to find the equation of a line through the point minus 1, 2, that passes through the intersection of 2x plus y minus 5 and x minus 3y plus 1 equals 0, how would we go about it? Quickly, we'll note that our lines are in general form. Now the first thing we're going to do is we're going to introduce a variable called k. So we're going to write our first line plus k times the second line and let that equal 0. And what we're going to do here is sub in our point, the point that was given, so negative 1 and 2, and that's going to allow us to solve for k because it will be the only remaining variable. So solving for k, we get negative 5 over 6. We now take this back to the original equation, leaving the x and y as variables and adding that in. So upon adding in k, we then expand the brackets, collect our like terms, and rearrange it in terms of x and y, and we get the equation of the line. So have a go rearranging this for yourself. It's quite a useful method. Now we're almost done. I'm just quickly going to run through a past HSC question to finish up. So this came from 1997 and was question 5, so about in the middle of the paper. Not too hard to start with, but covers many of the results that we discussed today. So here's our question. We can see already it's using many of the ideas that we've discussed. So we've got a square, we've got some lines that are equal to each other, we can see that we're being asked about congruent triangles in the first part, and then proving the size of a certain angle. So the first thing to do with this kind of question that I always recommend is to very, very carefully read that first sentence that's given to you. The amount of information in there is everything you need, and everything that's there is there for a reason. So use a highlighter, use a pen, whatever you're comfortable with, and really make sure you get the important information that's given to you. So what I would do is you've got here that A, B, C, D is a square. May seem obvious, but that's telling you straight away that all your sides are going to be equal, and also all these angles are going to be 90 degrees. So you may want to mark that on the diagram at this stage. We've then got that P, Q and R lie on AB, BC and CD respectively. Now there's not much we can mark on the diagram from that, but just as long as we're aware of it. And then we're told that AP is equal to BQ is equal to CR. So, and then again, that's marked on the diagram for us, so we can continue with the question at this stage. Now, I sometimes prefer, before I start writing things down madly, to have a read of the entire question, because you don't want to prove the second part in your first part and have to rewrite it out again. So read all parts of the question and then come back and start tackling it one step at a time. So I'll go through the solution to this question on the next slide. If you want to have a go at it yourself first, you can pause the video. So the first thing we do is that we know that AB is equal to BC, since, like I said, they're the sides of the square. So that's going to follow on quite quickly if you've marked that on your diagram, having, like I said previously, learnt those the properties of various shapes. We then know that AP is equal to BQ, because this was given in the question. And as you can see in the brackets, this solution's taken from the HSE past paper book. So this is the required layout of your geometric proof. So we need to say why we've stated something. And if that was given in the question, then simply putting given or from data will suffice. So we can now say that therefore if we take AB minus AP, that should be equal to BC minus BQ. And there's nothing we need to state for this because we've simply taken it from our previous statement. Therefore, simply by rearranging, we've got the BP is equal to QC. And we can see this clearly by looking back onto the diagram. So now getting to the point of the question, which was to prove that the two triangles were congruent. So looking at triangles PBQ and QCR, we can see that BQ equals CR, that was given, and that angle PBQ is equal to angle QCR, which is 90 degrees, because ABDC is a square. So again, we need to make that statement. And then, based on what we proved above, we've now been given that a second side is equal, and that leaves us to our side angle side proof, all that was required for the question. So if we break it down step by step, it's not too bad, and we can continue with the rest of the paper. So on to the second part of the question. We needed to prove that an angle was a right angle. So we know that angle BQP is equal to angle QRC because they follow from the angles of the congruent triangles. So here's another thing. If you for some reason can't do the first part of this question, it's okay to assume for the second part that those two triangles are congruent since you are asked to prove it. So then you can use that information to help you with the second part of the question. There's no point wasting marks on this if you could do it, but you just couldn't do the first part. So we then know that angle CQR and angle QRC must be equal to 90 degrees due to the angle sum of triangle QRC. So therefore, we've got the QRC and BQP are equal to 90 degrees. PQR is equal to 180 degrees minus 90 degrees, as BC is a straight line. And there we go, our proof falls out. Now I've included for you the notes from the marking centre, so this again just reiterates what is required to maximise those marks and where most students went wrong. So some people find these quite helpful to look for, but they can be found off the Board of Studies website. Alright, well thanks for listening and I'll see you next time.